So we were talking about pointers. Pointers in memory. How is memory arranged inside of our programs? How can we go to places? It's all just one big table of addresses to values, right? How can we go to an address and pick out the value there? We had to use a pointer. A pointer saves the address of somebody else. And the types got very wonky and important. Like if you wanted to hold the address of an int, you needed an int star, right? If you wanted to hold the address of an int, you needed an int star star. The ampersand was overloaded. It was just a bad time, but we'll get used to it. All right, we'll get used to it. And before we go to this question, just to make sure we remember things, I want to talk about your next midterm, because we're in week 10 right now, week 10. Reminder, you have a test coming up soon. There, you can't miss it now. So we're in week 10, midterm is week 12. All right, midterm 2 will be week 12, so I'll release so many of these things. Just that and that right now. Actually, let me make sure I didn't accidentally release too much for my other class. Okay, cool. All right. Yeah, so midterm 2 info and extra credit assignment. It's all the same as midterm 1. We just have to have another one, sadly. So it'll be week 12 or week 10. So the latest possible day is going to be the Thursday, so the 27th. That's when it's going to be. It'll be class time on the 27th. And yeah, here are all the topics. Pretty standard as all the stuff that we've been covering, essentially. Everything builds on top of itself, so be ready to write loops, even though those were on midterm 1, right? All that kind of stuff. That's how the class works. Here are some topics that you should expect to see and be familiar with. Here are, and here's a sample exam. Okay, so study that, and you should do all right. Any questions about the logistics midterm 2? Very similar to midterm 1, just more topics to test now. All right, and with every midterm, we have an extra credit opportunity. So just the same as before, please make a review video for topics that might appear on midterm 2. All right, this will be due midnight the day before the midterm, so October 26th at 11:59, because the test is on the 27th. So get that in if you'd like your extra credit. Remember, make something cool and new, explain the concepts to your peers, just like you did last time. All right, if you want the full extra credit, 20 minutes for your video. If you want half of that, make a 10-minute video. Okay, so that is the plan for that one, and that is the due date. Any questions about that? Now that you've done it once, it's pretty easy for me to explain it now for the second time. Okay, so take a look at those things, and that should be that. So that's midterm 2. Don't forget about it. It is 2 weeks and 2 days from now. All right, are we good to get into the actual lecture now? Well, let's do it. So, all right, here's just a question to make sure you remember something from Pointerland. So, all right, here's question 1 for you. I'll give you question 1 first, but think about both of these when I put you into your peer instruction groups and have you think about it. So, question 1, if I use a star in the type of a variable, right? If I say int star, and I like make a variable called p and set it to something, what does that star mean? And then question 2 is, if I use a star somewhere other than a type, like, I don't know, here, star p equals star p plus 1, I used it twice, both outside of the name of the type, what does it mean there? So question 1, which of these does it mean? 1 or 2, address of, dereference. Question 2, what does it mean? So let's do question 1 first on our bi-clicker, but I want you to think about both when I send you into rooms. We'll just do them right after each other, okay? So let's go there, and I'll give you a couple minutes to think about the answer to both of these. Okay, so but enter in the first answer, please, once you come to a consensus, right? If I use star in a variable's type, what does it mean? If I use a star somewhere other than a type, what does it mean? Do you remember our terms? Let's do a 2-minute timer. Another 15 seconds or so. Please enter in also your answer for just one, and then I'll do two right after it. All right, let's see what we're thinking. So if I use a star in a variable's type, what in the world does that mean? Pointer to, address of, or dereference? Boop. That's a beautiful looking graph, but not what I hoped to see. The answer is A, though. So the majority does win, if that's even a majority. A is the answer. That's a pointer to. So you read it backwards. I am making a box in memory that's going to hold the address of an int. P is, you read it backwards. P is a pointer to an int. I'm making a pointer when I use it in a type. That's the type of something. It's a pointer type. Okay, are there any questions about that? For those of us who did not get it right. Was it just a question of remembering the terms, or is there something a bit more insidious going on? Any questions? All right, so let's try number 2 now. If I use a star somewhere other than a type, what does it mean? Hide results. Take like, I don't know, 15 seconds to get your answer in. I assume we had it ready, right? Somewhere other than a type. So in that second line, star p equals star p plus 1, what does that do? What does the star mean there? All right. Ooh, this is another pretty graph. But it is, we do have a majority on C, and C is in fact the answer. So good job for the C people. It is dereferencing. That's what that means. It means follow the pointer, go to the box that it's pointing to, get the value or set the value. Here it's getting it, here it's setting it. And that means dereference. I want to dereference something. So what is the address of operator? Which one was that? That's the ampersand. Good. Yeah, so that's if I want the address of something. Like I have int x, and I want the address of it, I say ampersand x. I could set that into int star p if I wanted to. Int star p, because p is capable of holding the address of an int. P is a pointer to an int. I can set that to the address of x. So essentially, when you use the ampersand, you take the type of that thing, and you add a star to the end of it, right? Because I just had an int. I just made an int star because I was asking for its address. A pointer to an int. That's an int star. Okay, so that would be address of. That's what the ampersand is doing there. All right, yeah, so are there any questions about these 3 words? Because I'm going to be using them forever from now on. I want to make sure we're comfortable with them. Or maybe it's just a matter of me using them more. And then you'll get used to them too. Very good to keep going. All right, because I want to tell you about a magical place that we have not gone to yet that has to do with pointers. We had to learn it first. It's called the heap, which is a fun little metaphor. You can think of it like a pile of stuff, like in your room or something, and you just pile onto it more and more stuff. That's a place where you can make some memory. You can clean up your heap if you do laundry or something. But it's a place where you can store stuff. All right, it's kind of like a global variable. All right, so let's remember what global variables are first, because heap stuff is going to be very similar to a global variable, just in a different way. Okay, so Yeah. Remember that globals are a way to make a variable that lives forever. All right. That's one way to make something that lives forever. The other way is to use the heap. So anything that you make inside of a function, like inside of main, inside of a foo function, whatever you were writing, any variable that you define inside of a function is a local variable, right? It only lives for the life of that function. It dies once it returns. To make a global variable, you just declare it outside of any function. So I can make a big long array of size 1 million ints. I put that outside. I can make a global variable that's just a normal int. Global equals 42 or something. I don't know. These are global variables. They live for the life of the program. Any function can ask about them and touch them. They just live forever, right? And so to talk about that in terms of memory, all global variables are allocated, that's the fancy term, spaces being made for them in memory for you as the program begins. So all global variables, they are allocated, that is made in memory, right as the program begins, all right? And they live up until the end of the program because anybody's allowed to use it. You can't like get rid of it in between. You have to let them live for the life of the program. That's what globals are good for, all right? But that's also what they're bad for. Because they live forever, they waste a lot of space in your memory. So take this giant array, for example. That's like, I don't know, it's actually not that big. It's like 4 megabytes or something. But you can pretend that you're writing some program that needs this giant array on like a very small processor, like inside of a pacemaker or something, some embedded device where you don't have a lot of memory, right? Maybe for your program, you only needed that giant array for like the first half. You're like doing some data crunching for the first half of your program. You needed this giant array for that. But then once you have the answer, you don't need the array anymore. Does that scenario make sense to us? You only needed that large array for half of the program. Everybody needed to touch it for that first half, so you made it a global variable. But after that's over, after you have the answer that you've calculated from it, you don't need the array anymore. But sadly, it's going to live forever, right? It lives for the life of the program. What did I just do? There. No? That's impressive. All right. I cannot, it doesn't remember that I drew that. Oh. It doesn't even think it's there. All right, that's a fun bug in PowerPoint. What if I draw something else? Does it remember? No. Oh, it keeps that one too. Okay, let's restart PowerPoint before this gets worse. Sorry about that. But that's the scenario. If I can't erase things, I'm going to have a very bad time for the rest of this lecture. There we go. All right. Can I draw and undo? There we go. Okay. So maybe you only need that array for half of the program. It's a waste of space. You could be using that space for other things. You would run out of memory otherwise. Okay? Does the scenario make enough sense to us? So I would like to have something that's like a global variable, but I only want it to last as long as I ask it to last. That's what I'd like. We can actually make that happen. We can use this thing called the heap. All right? So let me tell you how your program is arranged in memory when you load it. That's going to help when we talk about it. Here's the magical heap, but the rest of the stuff is stuff you already know. So when you start a program, you double-click it, you say // name of your program, hit enter. It gets loaded into memory, and here's what it looks like. It looks like this. It has all these sections, right? The first section of your code in memory at like low addresses, it's like here's the lowest address, here's the highest address. At the low addresses is the actual program itself. You have to store the code for your program somewhere. It has to live in memory too. It's just we don't think of it that way. But it needs to go in memory, and there's a space made for it. It's called the text section of your program. It's read-only because you do not want to mess with your program as it's running. You would change the instructions, like you change a plus to a minus. That doesn't make sense. So it's a read-only section of your memory. You can't try and change it. It's called the text section. So the code for your program lives in memory. That's the first part of the program. Then there's a separate place in memory just for your global variables because they have to live forever, so space gets made for them right immediately. It's like all of these addresses, they're for the global variables. They live forever. They can all be right next to each other. Okay? That's what happens there. And then there's a third chunk of memory that's shared by two people. So here's your global data. You got your global variable, your global array like I was drawing on the previous slide. Next you have the last chunk, which is shared by the heap and the stack. The stack we know, that's your functions being called and returning. So here's main way down here on the stack, and main might call foo might call bar or something. And so space gets made dynamically as things get called, right? Because you need more stack room to store how to return back to the function before you. So this chunk of memory grows and shrinks as functions get called and return, right? So that's what the stack looks like. You know it and you love it now. That's where all your local variables live for all your functions. So maybe like main needs this variable. We need to make space for it. We need to move this stack end, the end of it. So we need some variables, bar needs some variables, etc. And then when they return, space goes back into this chunk, back for other people to use. So yeah, the stack looks like this. It grows towards lower addresses inside of like modern operating systems, which is weird to think about, but that's okay. Then the stack is like fighting for space with this thing called the heap. The heap is growing towards higher addresses down this way. The heap holds dynamically allocated data. That's what it's called. It's essentially means I can make a big long array on the fly and have it live here forever until I tell it to delete itself. That's what you get with the heap. You can make stuff, have it live for as long as you want it to, and then you can tell it to delete itself, and you have that space again. Okay? That's what I mean by dynamically allocating things. All right? And so you can dynamically allocate a bunch of stuff, some arrays, blah, 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 and that grows the heap down this way. And that's fighting with all the functions being called and all their local variables being stored. If you ever allocate too much stuff on the heap or call too many functions in a chain, then you've run out of memory. That's what it means to run out of memory. If the stack or heap ever meet, there's no space to store the next thing. And so your program is out of memory, you get a runtime error, and it just stops. Okay? So stack and heap share the same chunk. The stack grows down towards lower addresses, and the heap grows up. They fight for space. And that's how it works. The heap is just a place where I can make some memory that lives for a little while, and once I'm done with it, I can delete it so that I can use that space again. It's kind of like global variables in that sense, but I can actually get rid of them. I can't delete a big long array in the global section, but I can in the heap. Okay? Are there any questions about this diagram, that idea? Again, I haven't really fully explained the heap to you, but this is kind of what a program looks like in memory. That's what I want you to understand. All right. If we're good with that, where do I want to be? Yeah, this is fine. So yeah, the heap is a lovely place where you can make memory. You can allocate memory, make some room for something, and you can get rid of that memory that you have previously allocated. All right, just when you say so. You can essentially make a global variable if you never tell it to delete itself, which is pretty nice. So like globals, heap memory can potentially live forever. You can share it across any function. It lives for as long as you ask it to. It's never going away. But you can also delete it. You can also remove stuff when you want to remove stuff. Okay? And then also, you don't have to say up front, like as you compile your program, how many things you need. You can just, as your program's running, make it something, make enough space for your current run of the program. And here's an example of that. So say you have a number n, like the user, you ask the user, hey, how many things do you want to store in my big long array? And they say n things. You get that n from the user. And they can either type 42, they can type 1,042. You get this as the program's running. You don't know ahead of time, right, what the user's going to type. You can go on the heap and make an array of exactly that size, whatever the user gave you. That's beautiful. That's what you can do with the heap. And then you can also delete it. Okay? So let's see. How do I want to do that? Yeah, no. That's all right. So does that make enough sense, this idea of I can make memory and I can also get rid of it. It can live for as long as I ask it to. Are we ready to see how that works in C++? All right, let's make sure I know where I'm going with this. So to make something on the heap, you use what's called the new operator. You say new, and then you give the name of a type, because C++ has to know how much memory to allocate for you. Like an int is 4 bytes, a double is 8 bytes. You have to say what type of thing, so it knows how much memory to make for you. But here's what happens. You say new, and then the name of a type, like new int, and that goes to the heap, and it makes you a brand new place that holds enough room to have an int in it. New int returns you back a pointer to an integer that it made for you on the heap. All right? So this line is how you would do it. You'd say int star n equals new int. That gives you back one new integer on the heap. It makes an int for you, and it gives you back its address, because there's no way to name something on the heap other than knowing about its address. So here's what's going on the stack and on the heap. So the stack is like this local variable n. It's a pointer, right? Anything with a name lives on the stack. So here's n. It lives in like main's stack frame or something. And then on the heap, once you say new int, it makes a brand new box in memory that holds an int. It makes 4 bytes. And so it's shiny and new. When you say new int, it does this. It makes a brand new box on the heap, space that wasn't there before in your program. And like it's set to nothingness, it's set to garbage, but it has an address, address 100. And that's what's given back to you by new int, and that you can place into your local variable to remember where on the heap this thing was made. So this will set n equal to 100, assuming that's where it lives on the heap, and that's what this line will do. Does that idea make sense to us? So new int gives us back a brand new integer on the heap. It makes this box for us, and it gives us back its address that we can store somewhere else. And as long as you have that address, you can touch this memory. It lives in a separate place, separate from any other like local variable. That's the stack. It can live for the life of the program unless you want to get rid of it. Okay? So you say the name of the type, and that is going to make you an int star. It gives you a pointer to that int that it made for you. Okay? And then you can say star n equals 42 as you would with any other pointer, and you could set that memory. And now it's holding 42 for as long as you want it to hold 42. Any questions about that? So let me try to give you a good example of what's going on with heap stuff. Dun, dun, dun. Maybe I'll make a simple example and then we'll beef it up to show you the true power of the heap. So I could do it as usual. I could be like int star, I don't know, n equals new int. This makes a brand new int on the heap. Make space for one int on the heap and save the address of it into n. Something like that. Okay? That's that one. And then I can set it to something and be like star n equals 42. See out star n. I just made space for something on the heap. Beautiful. And I'm setting it to 42. Using it as a normal pointer. And I'm not deallocating it, so I'm treating it like a global variable right now. It's just, it lives forever. It gets cleaned up when the program ends, of course. But here it is holding 42. Are there any questions about that? So I'm saying new int gives me back a pointer to an int, that shiny new box that it made on the heap. I'm saving that away in n. I can use that for as long as I want in between functions, if I want to. And yeah, there's me using it. I'm good with that? Good enough with that, at least. So the power is this can act like a global variable. So instead of making it all in main, let's introduce a new function. Let's be like int star make new int on heap. And let's move all this to here. Int star n equals new int. So here is a function that I can call. I'll be like make new int on heap. And it's going to make a new int on the heap. It will set it to 42. Here I am printing the value of n up in this function. But I can pass it around. I can pass this place on the heap around as long as I save the address where it lives. So how about this return? This function will return an int star. And I could also talk about it in main, int star p. I'll call it p down here. Return, and this needs to return n, of course. So return that int star. So it's going to return, it's going to mess with that place on the heap up here. It's going to give it back to main, and so I can use it down here too. Does that idea make sense? That's pretty nice to be able to do that. I can pass it around and use it like a global variable as long as I know that address. So I can say star p equals star p plus 1. That will affect this box on the heap that holds 42 right now. I just made it hold 43 down here in main though. So two separate places, two separate functions manipulating this heap thing. So yeah, star p, now it'll print 43. And so I've used it in two different places, two different functions. As long as I pass it around, I'm talking about the same place in memory. It's like a global variable in that sense. Are there any questions about that? So yeah, that's what the heap can do. Obviously, you usually want to make more than just a single integer on it. So I'll show you that in a second. But we just made some shiny, cool stuff. Now what happens when we're done with it? Like we use it for half the program or something. The flip side to new is called delete. If you would like to get rid of something you made on the heap, you say delete, and then you give the address of that thing. All right? Delete n is going to do this. If n should be a pointer to a place on the heap, you say delete n. It's going to go to that address and delete the memory there. So this line, assuming memory looks like this, is going to follow n. It's going to be like, all right, I point to address 100. Go to address 100, reclaim that memory. No longer exists. Right? Reclaim. And now if I say new int again, it might reuse this space. That's the beauty of the heap. You can reuse that space so that you don't run out of memory. You should clean up after yourself. Okay? So you say delete n. That is a pointer to the place where you want to reclaim. Okay? Any questions about that idea? Once you're done with something, like, all right, I used n up here, I used this heap place up here in this function, I used it down here in main, I'm done now with this int. Now I should delete it. Once you're done with heap memory, make sure to delete it. And you just give the address of the place in memory where you want to delete. Up here it was n, but down here I'm saving it in p, the address of that place on the heap, so I'll say delete p. And the program doesn't change, but I've now cleaned up after myself completely. So that is the full program, I believe. Can't show it to you very well. There we go. I made it here. It got born, that int, that global kind of thing, got made up here in the new call. And down here in the delete is where it got reclaimed. And it lived between those two functions. Beautiful. Any questions about that? All right. So if we're good with that, why does it type CPP? If we're okay with that, let me show you how to make bigger things. Like, how do we make this giant array on the heap of this arbitrary size? Because that's what heaps are good for, making fancy types, bigger things. The first secret to making something on the heap is noticing that an array is really just a pointer, which is pretty funny because we've been using arrays this whole time. You've secretly been doing pointer stuff back when we learned arrays. So when you say int r42, I usually draw it like this. R, it has size 42, right? It's got a bunch of stuff in it. I don't know what you want to put in your array. It's got 42 elements, of course. You can store like 1, 2, and 3, whatever you'd like to store, ... But really, secretly, like we've been interacting with the array like this, like set R of 1 to 2, cout R of like 0. We've been interacting with our array like this, but you can actually just say R. You can just say R by itself, and that is a pointer, in fact. If you just say R by itself, that is secretly a pointer to the beginning of this array. So really, I shouldn't be drawing it like this. That was just to help you. Really, what R is, let's pretend this is address 100, 104, 108, because the array stuff goes in order. R, just by itself, is secretly a pointer to the start of the array. Boop. It's really doing that. And if you don't believe me, let me show you. Arrays.cpp. So, I don't know, int r equals, I don't want to mess up our indices. Let's do array r equals 5, 6, 7. That's apparently what I did last time. And so, sure, I can print r of 0. That will print the 5. But what if I just print r? Ooh. What is r? That is an address. Ooh, whose address? It's the address of the first element in the array. So I can do it like this. Address of R0. Those should be the same number. And lo and behold, they are. Different every time you run the program, of course, but that doesn't matter. They're the same place. R is the address of the 0th element of the array. Just say R. It is a pointer to your first element. And so there's another way to get the 1. In our case, there's another way to get this 5 because R is pointing to it. Instead of couting R of 0, I can say, and this is fun, I can say cout of star R. Can't I? Because R is pointing to this first element, and the first element holds 1. If I follow the pointer with a star, I'll get the 1 out. 1i. That's pretty cool. Oops. And by 1 I mean 5. That's the 0th element here. Are there any questions about that? So star R is R0. Therefore, are we good with that? That's a bit weird, but that is totally possible. Let's see, what else can I do? I can put, do I want to do this now or later? Yeah, if this is really, if R is just a pointer to the beginning of the array, maybe I can do this, and this will work too. I can say int star p, well, give it a pointer to an int. That's what R is. R is a pointer to the first int in this array. So I can set p to R, which is the address of the first element, and then, of course, I can say star p to get the 5 out again, just like I was using star R. But there's also a flip side to this notation. Any pointer can be interpreted as an array because of this idea. So I can say cout of p of 2. P is just a pointer. But I can treat it like an integer array. And if it is 1, it'll actually do the right thing. This should print 7. So this is just syntax. It's a bit weird. But if I have a pointer to the start of an array or anywhere in an array, I can treat that pointer like an array. I can use my bracket syntax that I know and love. That's going to allow us to make arrays on the heap. Okay, are there any questions about this idea? So R by itself is a pointer to its first element, so star R is going to give me that first element. And if I make a pointer to an array, like its 0th element, I can use array style indexing, and indices, and like go into that array. Go over here, even though P was pointing to the start of it. I can use a pointer like an array. Hopefully you should be actually using an array with that pointer, but this is totally possible. All right, if we're happy with that. There's also the idea, there's a concept of pointer arithmetic, which gets extra fun. So let's say this was our array, 5, 6, 7. That was R. And so if I said, let's try and give myself some room for this. Here's my array. If I say R, let's say this address is, I don't know, 10, 14, 18 or something. If I just say R is a pointer to this element, the 0th element. Actually, R plus 1 is a pointer to the next element, which doesn't make sense. You might think that would give you address 11, but no, it goes one more int, so that's 4 bytes. So R plus 1 will point to the next integer in the array, okay? So secretly, this syntax, this R of 1 syntax, is being translated into R plus 1 dereferenced. That is the secret, okay? So here's the pointer, this is R. R plus 1 is pointing to the next element in the array, one after, all right? And yeah, this works because R is the starting address of the array, and 1 is the offset from that starting address. C++ knows to go one int later, which is 4 bytes long, right? Not just 1 byte later. That is something you'll definitely have to get used to, sadly, but this is how it works, all right? So in that case, this is secretly being translated into star p plus 2, and if I want to access the element of R1, I could of course see out R1, or this is being translated into R plus 1 dereferenced. Right? So this is equivalent to R of 1. That's actually what it's being translated into when it's being compiled. So there is my printing of the 6s. Same place. Same number. You good with that? That's pretty weird, but pretty cool. So that's what pointer arithmetic does. You can add to a pointer. You can add some numbers to a pointer and move around from a starting address. And the reason you'd want to do that is when you have an array. A bunch of things right next to themselves. Okay? You can also do this for C strings, because what is a C string but a special kind of character array? It's just an array of characters with that secret null terminator character at the end. Remember that? And so finally, we come full circle. I can tell you why we have to say, everybody does say, char star argv bracket bracket. Okay? Because a C string is just a char bracket bracket, char star is equivalent to that. And so now we know why argv is an array of C strings. It's an array of char arrays. You could just say, what is an array but a pointer to its first element? That only took, I don't know, a month to get to. But that is why. That's why we can say char star. It's an array of C strings. Any questions about any of that? That's a bit weird, I know. But that's the syntax. Pointers are everywhere. Right? Now that we have this syntax under our belt, I can teach you how to make things on the heap. I can teach you how to make arrays on the heap. I guess so. If you want to make an array on the heap, you say new. You say new int, and then, if you want an array of ints, you say new int at least. And then you say in brackets how big you want that thing to be. Okay? This could be a variable. Doesn't matter. I can say new int 42, new int n, if n was a number that I got from the user. It'll make an array on the heap just like this, and it'll store its starting address. It gives you back its starting address. That's how it has to work. Okay? So stack. This is what happens when you run this line. Stack heap. So P is something with a name, so P is a pointer that lives on the stack somewhere. And you say new int of size 42, that makes you a brand new size 42 array. Like here's address 100, address 104, ... 42 long. Brand new on the heap. That's what that does for you. And P will hold, and new int gives you back, the starting address of this thing. So it starts at address 100, so P will get set to address 100, and it will point to that starting of the array on the heap. And now you can use it like an array with the array-like syntax. You can be like P of 0 equals 42, because you can work with pointers like arrays if they are arrays. That's beautiful. And then once you're done, because it's just an int star, C++ doesn't know, like, if you want to delete it, Was it just a single int on the heap, or was it an array of ints? So you have to tell C++, no, this was an array, please delete it. Delete the whole thing. So you have to say delete bracket bracket. That deletes the entire array. That's what that will do, that line, right? So with that in mind, let's do that. Let's make an array. So, I don't know, int star q equals new int, size 42. So q will hold now. Q holds the address of the first element in this size 42 array. All right? That we just made on the heap. Whee! That's what happens there in star q. There we go. And now I can use it like an array. I can be like, okay, q of 5 equals 55. I don't know. See out q of 5. I can use it like an array for as long as I need to. And once I'm done with it, I can delete bracket bracket it. So there's my 55 being printed. I'm using this array that I made on the heap. Once I'm done with it, I can pass it around between functions. I say delete bracket bracket q. Right? Remember the brackets for an array. Okay, so that's how you make an array on the heap. Gives you back its starting address. You can use it like an array, and then you delete bracket bracket it when you're done. Any questions about that idea? All right, I now have a question for you. Try your best. It's a hard question, but that's why I'm asking it in class. So here are 3 lines of code. Consider each of them. I would like you, get out a piece of paper as a group or open up Paint or something, draw what memory looks like after those 3 lines have been executed, each of these 3 right here. Draw the state of memory after those lines have been executed. Also specify which boxes are on the heap versus which are on the stack, like which are local variables, which belong on the heap, which boxes are heap memory. So section it off like that. And then also draw what happens. You can just draw an X, right? Draw what happens when you say delete P. If you were to add that line to the very end, what would happen? Which box or boxes would have an X through them? What memory would get reclaimed and deleted? Okay? Are there any questions about the question? So I'm asking you to draw a picture like the kinds that I've been drawing. Going to make a new int star on the heap. You're going to make a new int. And then you're going to say delete P. Okay? And P is an int star star, interestingly enough. So a lot of practice with a lot of weird pointery things. So I'll give you a few minutes to try this, and please yell at me if you have any questions. So draw a pretty picture, please. Take another 30 seconds to try and draw your pretty artwork, and then we'll talk about it. All right. So let's see what we're thinking. First of all, how many boxes total did we draw? How many boxes total should there be? Did we get that? We're not sure even of the number of boxes, number of places being made in memory on the stack or on the heap. Just one big one. That's definitely a possibility. And yeah, we're doing stuff with P, dereferencing P. First, and then also, how many boxes are on the stack versus how many were on the heap? That's another thing to consider. So it sounds like we are very confused, and so let me start drawing stuff. And I want you to come back and study this example. This is a great example. It might be a little too challenging right now, but it's a great place to study. All right, that's why I gave it. So first of all, stack versus heap. It's an easy way to remember what's on the stack. All of your local variables, they have names. The only thing with a name in this code is P. P must live on the stack then. Like I'm in main, I make P. There it is. It's a local variable. It's local to somebody. Because all this code is happening one after another inside of a function somewhere. So here's P. It must live on the stack. Okay? And then P is being set to a new int star. Whenever you say new, you make something on the heap, right? So I'm saying new twice. I'm making two things on the heap. There will be 3 boxes total after I'm done drawing. So I make a new int star. Interesting. All right. So I just made a box on the heap that holds an int star. This is its type, right? And so if I want to latch onto this and hold where it is, because new gives me back the place that it got made, the address of it, I'm asking for an int star. It's going to give me back the address of an int star. It's going to give me back an int star star. Does that make sense? The type of this must be int star star. So this over here is int star star. That's what P is, and let's pretend this is address 100. So P will hold 100. I have a place on the heap that holds a pointer to an int. All right? And then I say star P, which is going to follow this pointer and set the contents of that box to something. It's going to set it to new int, which is going to be an address that's given back to me after making a brand new int on the heap. Int star. All right? So I make another box on the heap that holds just an int. This is an int down here. And this new int gives back its address. I'm saving that in star P, which is right here. Do we see that? Are we following that? So maybe this is address 200. That means I'm setting star P, which is this, to 200. I'm saving the address of an int right here, 200, and it's pointing like that to that last int that I just made for myself. And the types all check out because I am storing the address of an int right here, right? It's an int star. And here's my int. That's its address. Are there any questions about that? I haven't done the last line yet, but that's the easiest line. Star star P equals 42. Well, all right, start at P. Do one star, that gets me here. Do another star, all right, dereference that gets me here. And set that thing to 42. So that is what should happen in memory when you run those 3 lines. So what questions do we have about that? So we were definitely having some trouble, I think. Is it all resolved now that I gave you the answer, or is there anything still that is confusing that I can talk about? Feel free to think of a question. We can come back to this slide. And then when you say delete P, remember what delete does. It's not going to delete this. That's stack memory. It never goes away until a function returns. It's not going to delete both of these. It's just going to delete one place that we made on the heap for ourselves. Where's that? It gets rid of memory on the heap. It goes to that place on the heap and deletes the memory there. So if I ask you to delete P, it's looking at this address because that's what's stored in P. All right, address 100, delete that. Here's the thing at address 100. This is what's going away. Not this one. Just that one. Just that int star. If I wanted to delete this one, I have to say like delete star P or something. That would actually get that address 200 to be deleted. So that is the final answer. That's all 3 lines and a delete P at the end. That's exactly what will happen in memory. Any questions before we move on? Because actually something horrible just happened with this example. I just kind of like lost access to this 42. Like there's no way to get to it anymore. That's no fun. That's something called a memory leak. Maybe you've heard that term before. A memory leak is when you lose access to something in your program. It's memory. And that data, that memory never goes away. It never gets reclaimed, and you just don't have a way to get to it anymore. So you can't even use it. Can't make use of it. And it happens when you use the heap. If you forget about something, you don't delete it. So here's a very simple example of how to accidentally lose something on the heap. So here is a memory leak. It will be, all right, let's say int star I equals new int. So that is making an I variable on the stack. And here's a brand new shiny int on the heap. Maybe address 100. So I will hold 100 and it'll point like that. And it was shiny and new. Okay. So there's my new int. That's the first line. Then I say star I equals 42. So I use this box. I set it to 42. And then I come along and I say right here, I equals new int. Oh man. That's unfortunate. So when I say I equals new int, I just make a brand new place on the heap, right? That's what new int does. It makes a brand new spot on the heap and it gives back its address. Maybe its address is 200. 200. And so what I just did when I say I equals new int, I just did that. I now holds 200. It's pointing to this place. It's no longer pointing to this place. You see that? And now if I say star I can't get back to this original int. I get to this one. I say star I equals 43. Now I'm setting this to 43. I have no way of knowing where this place is because I don't save the address anywhere. I lost the one place I saved that address. You see that? So I lost access to the first int. It's going to live until the program ends now. I've leaked that memory. I can't get to it. I can't use it. It's just stuck in memory. I can't use it for anything. So this line right here causes a memory leak. Okay. If you wanted to save this, you need to store in between here this old address, this address 100, so that you can get back to that place, or delete it in between. Do something like that. But do we see the problem? I lost the one way to get to that first int that I made on the heap. That is a memory leak. If there are enough memory leaks in a program, it just starts running out of memory slowly but surely, and eventually it'll crash. A lot of large software has a bunch of memory leaks. Maybe have been on the receiving end of a memory leak, and you've had a program crash on you for no reason. Maybe there was a leak and it just ran out of memory. All right. So, yeah. Any questions about that before I move on to a couple final topics? I think I have just 2 more programs that I want to write. Let's write a program that actually uses the heap for something, something non-trivial. So let's ask the user for a number, and we'll make an array of size n on the heap, and then we'll ask the user for n things, and we'll fill up the array, and maybe then, I don't know, we'll calculate the sum of that giant array that the user asked us to fill, and then we'll delete it. So something that involves us using heap memory to do something real. All right, so let's do that. Array sum.cvp. So let us ask the user for how many things they want to fill the array with. So enter the array size. So we'll get that. And then let's make an array of that size, of that many ints on the heap. Make an array of n ints on the heap. And then we have to do like this, right? Int star, let's call it r, equals new int of size n. Whatever the user gave us. Could be 1,000,000, could be 10. Could be 1. And we fill it. We ask the user, okay, you asked for that many things. Please tell me what they should be. Fill it. So what are the valid indices for int I equals 0 to n minus 1? So strictly less than n, I plus plus. Oops, not p. And so we'll just like get every element, next element, cout, enter the next element, and then we'll get it, and then we'll put it in the array, r of I equals next element. So now I have, after this loop completes, I have a value inside of this heap array at every index, and let's just calculate the sum of everything, sum everything. Maybe you want to calculate the average or something after that. So int sum equals 0, and then we can go through it all over again. I'll just steal the for loop for fun. And we'd be like sum plus equals r of I. And remember that r is an array on the heap. It's an int star, really. We're using it like an array because it is one. And so then I have my sum. I need to output the sums. And then I should delete the array. So I'd be like, I can say this, delete bracket bracket r, because it's an array on the heap. But actually, pretend that I was doing a lot fancier of things. This delete is actually a little late. I'm done using the array after this loop. This is going through the array. I don't actually need the array anymore when I print the sum. So this could go up here. I'm now done with r. Done with r, delete bracket bracket it. Okay? And so then we output the sum, but here I am making it on the heap of that arbitrary size n. Here I am using it, doing stuff, filling it, and there I am deleting it. All right? Are there any questions about that idea? This could get a lot more fancy. I think you can imagine. You could pass it around between functions because it is on the heap. But at least this is a more non-trivial example. So enter the array size, I don't know, 5, 1, 2, 3, 4, 5. And apparently the sum of 1, 2, 3, 4, 5 is 15. Yeah, it's 6 times 5 divided by 2. That checks out. So I'm making something on the heap, I'm using it, I'm deleting it. And this works for any size. Be size 1,000,000, size 3. 1, 2, 3. That's 6. Any questions about that? Making an array on the heap with new, deleting it after using it with delete bracket bracket. Alrighty then. So yeah, you might wonder, like, why not just use vectors? Why am I going to ever need this? And the best answer to that question is going to come in CSCI 41. The reason we need the heap, the reason we need pointers badly. And I'm going to try to give you a taste of it now, but here I've made this meme for us. Secretly, when you use a vector, when you use a string, all these C++ data types that we love, we can push back, we can add and use easy things, they're all secretly using dynamically allocated arrays. If you make a vector of ints, it's secretly making an array on the heap, and it's keeping track of it for you. If it ever runs out of space, it makes a brand new one that's double the size. You will program your own vectors if you take my CSCI 41 class. Strings, they're just using a dynamically allocated array on the heap of chars, right? That's all they need. If you want to add to a string, it's going to make some extra space for that extra string that you're adding to the end, right? That's what strings do. You've secretly been using the heap. It's just been done for you through the magic of all these member functions inside of vectors and strings and things. Okay? So that's a reason to learn it, I think. So one day you might want to make your own, or in a data structures class, you will be forced to make your own. Any questions about that? Does that make enough sense? So you've secretly been using all this stuff this whole time. And before we close, this is a CSCI 41 topic that I want to tell you now. I'm not going to test you on this. Your book does talk about it, and I think you might have some little Zybooks questions about it. So I will ask you to read it, but this is a CSCI 41 topic, and I won't be testing you on it. So linked lists are a great answer to this question. Like, why will I ever need a pointer? Why can't I just use references everywhere? What's the point of null? Why can't I just use references? Why can't I just never use the heap, make everything on the stack? Everything can be a local variable or a global variable. Linked lists are one good answer. All right, so here's a very quick overview to linked lists. See your book for more, or see CSCI 41 for more as well. All right, so a linked list is a data structure. It's very similar to an array in that it holds a bunch of stuff in order, but it's made in a different way. So a linked list, it's a data structure. It consists of things called nodes that hold the following. They hold, each node looks like this. It holds a single piece of data, like a 1, and then it also holds a pointer in its next bit. It holds a pointer to the next node in the list, which is funny. That's how it works. All right? So here's an array holding 1, 2, 3. We know how that works in memory. Here's a list holding 1, 2, 3. It's got a bunch of nodes. It has 3 nodes. The data portion of them is 1, 2, and 3. Again, I'm not testing you on this. That's a CSCI 41 topic. And then they hold a pointer to the next node. Boop. Boop. That's the next node on the list. Once you're at the end, you have to store, like, okay, I'm done. You hold, like, 0 or the null pointer. And all the time, pretty much all the time, all those nodes that you make and you add to your list are all in the heap. And you interact with them through, like, a stack variable that points to the start of it. Stack. Here's, like, your L variable. It points to the first node in this linked list. Okay? Linked lists, like this is the list 1, 2, 3 in order. You just got to, like, traverse all these pointers to iterate through it. Hopefully that makes enough sense. They are, like, competing with arrays and vectors in a sense. It's a lot easier to do some things with a linked list rather than with an array or with a vector. Here's one thing that's really, really easy to do in a linked list, but super hard to do in an array. Adding a brand new thing at the start. So for example, let's say I have my array 1, 2, 3, and then I'm actually required to have empty space if I want to add something to the front, right? Let's say I want to add 0 to the start of this array and retain everything else. What needs to happen? Well, I need to make room for that 0. I need to move this over here, this over here, this over here. I think you can imagine that's a huge pain if the array is huge. I've got to put 3 over here. I've got to move all the elements. 1. So now I have the 1, 2, 3 here, and I can put my 0 here finally. That's a lot of work. Okay? With the linked list, here's what you could do. Stack heap. Here's my list. It points to the beginning of the list node. It originally held 1 and 2 and 3, right, in that order. 1, 2, 3, null. If I want to add the 0 element at the start of the list, all I have to do, make a new node on the heap, put it at 0. I have this address at the start of the list. Reuse it to point as the next pointer there. Chop this one off, move it there. Like 4 lines of code to add something to the start of a linked list, rather than having to move a million elements over, shift them all by 1 inside of an array. So that's one thing that a linked list is really good at. And you will get used to all of this in CSCI 41 or when you read about it. But are there any questions about this right now? It's a fun little concept, but the world does not end with vectors. It does not end with arrays. There are things that are better for some things that you might want to do. And each of these nodes, here's what they look like, if you care. They're a struct node. They're made of, well, you have to hold on to your data, whatever you're holding on to. So int data, for example. Put anything here. Could be int char double. I'm holding ints. And then you have to store a pointer to the next node in the list. So this gets a little odd. We call it next, but the type of next is a node star. You're defining this struct and you're using it inside of itself. That's a little scary, but that's how it works. That's one good thing that heaps are good for, and one thing that pointers are good for. You're forced to use all of those in this data structure called a linked list, which you will become intimately familiar with one day, most likely. So yeah, that's my silly motivational example, just to make sure you understand why we're learning this stuff. Are we good to move on to one last thing that's going to help you on future labs that involve pointers? All right. So there's this cool thing called GDB. It's a program, and it's going to show you when and where errors occurred. Right? So you're going to mess up so much when you use pointers. Everybody does. I do all the time. When you use pointers and when you use the heap, you're going to get a bunch of seg faults, right? If not other things. GDB is a program that will help you. It stands for the GNU debugger. GDB. And GNU is a funny little acronym that I encourage you to look up on Wikipedia. It's a recursive acronym. It's made by the same people, GNU. Those are the people who made our compiler. Our G++ compiler stands for the GNU C++ compiler. So, same people. And what it does is you run your program in the debugger, and it gives you nice information about that program as it's running. It tells you, it's able to keep track of for you the values of all your variables. It remembers the line numbers where things happen, especially where runtime errors happened. Ooh, that's helpful. The only thing you have to remember when you want to use GDB is you have to compile with the -G flag to have it include like the line numbers inside of the program binary. So it adds the debugging information to your compiler program. So if you say you're compiling a program, you say G++ foo.cpp, normally you say this -o foo. Just add a -G here, and then you can run it in GDB, and it'll be happy. Okay? That's the new addition. And so let me give you a fun little example of using GDB. Oops, I have to delete that. That's no longer required. I'm going to make a program called segfault. That segfaults. Imagine that this was a more complicated program. So, I don't know. Let's have it go and do it in a function too, because that'll be extra fun. Void uh-oh. And I don't know, let's make int x equals 42, int star p equals null pointer, and then cout star p. Like I was supposed to set p to x's address, but I forgot. It's set to null right now, or some random address. This is going to segfault right here, right? Because p is pointing to nothing. It's going to stop the program with a runtime error. Segfault. And so we get this ugly error message, and we have no clue what happened, right? Enter the debugger. Enter GDB. So compile it like this, G++ -G, and then all the rest that you normally do. It makes a slightly bigger binary, but it remembers all of the debugging information, all the line numbers and stuff. And so instead of running it by itself, instead of saying ./segfault, which is just going to run it normally, you run it inside of GDB. GDB is a program. Just pretend to run it. Say the ./segfault. Just plop GDB at the front of that, and then press enter. And this will load it inside of the GDB program. Okay? And this will plot me and press return because it's going to tell me a bunch of stuff. Now I will have a GDB prompt down here. Okay? It gives me a GDB prompt. What do I want to do? Here's what you can do. You can say R to start running the program inside of the debugger. Hit enter, it's just like a command. You can also just type out run, but I'll say R for short. And then it starts running the program, and look at what it does. So starting program, blah, blah, blah. Program received this segmentation fault, and look at what it prints. The segmentation fault, oh, it happened in the uh-oh function on line 7. This line, and it prints it out to you, it's so nice. It says exactly the line where the segmentation fault occurred. Do we see how helpful this will be? Remember this. Come back to this slide, okay? Not only that, it can tell you how you got to the uh-oh function. If there's a bunch of different ways that it could be called, you say BT for backtrace. It shows you your stack. It's like, okay, I was in main. Line 11 is where I called uh-oh, and here's that call I was inside of. Here's uh-oh, okay? Then I was on line 7 of uh-oh. Shows you your stack. not only that, but it can print the value of any variable that is currently alive in your stack frame, or a global variable, whatever you want. So like, okay, the problem happened on this line. I think endl is fine. I think cout is fine. It must have been p. What's p? Print p. Oh, it was 0. That's null. That's what it shouldn't have been. That was the problem. It'll print the value of the variable when the error occurred. It'll also print anything else. If I want to print x, it's like, okay, what was the value of x when this error happened? You can imagine it could have gotten changed. Oh, it was 42. Maybe that's helpful for you. I don't know. You can print whatever you want out to see how this error occurred. And it'll stop the program on the line where the error happened, and you can learn all these wonderful things from it. Okay? So that's GDB in a nutshell. Please use it. It will save your life. So it makes things so much easier when you run into issues with pointers. Okay? And then once you're done with GDB, you just say quit. Quit or Control D, probably exit works too. And that's going to say, I am currently running your program inside of my program. Are you sure you want to exit? Because I'm going to stop that one too. And you just say, why? And then you're back. Then you can fix it, recompile, rerun, and be on your way. Any questions about that? Isn't that fun? So yeah, we've come a long way. You know a few reasons to learn pointers, but I promised you that you'd be able to understand this comic by the end, and I think you can now. So I believe that is everything that I wanted to show you today. We're going to have a new lab next time, and I'm pretty sure, yeah, that's going to be a Thursday problem. But yeah, it was just the lecture today. And that is officially all that I have.